Hello, everybody, to the super organized. Right, thank you for having me. We're going to have, am I good to go? So this is going to be a brief panel on NFV, Network Function Virtualization, and how it relates to KVM. I'd like to present my panelists here. My name is Dave Neary. I work for Red Hat, and that's all you need to know about me. I've got on the nearest me here, Vincent Jardin from Sixwind, a French-based company who works on data plane offloading, among other things. But is that good enough?
Yes, that's correct.
Gerardo Garcia from Telefonica, representing telco operators here. Jun Nakajima from Intel, who I think many of you already know, and Steve Gordon, who's a product manager for a lot of our compute stuff, including OpenStack, Nova, and you also PM for KVM? No. But he is responsible for a lot of the things that we're doing around NFV inside Red Hat. Without further ado, I would like to start off by asking Gerardo specifically. So I think a lot of the people in the KVM community maybe aren't aware of how big or how KVM will be used in the NFV use case. Could you give us an idea of really how big the opportunity is for the KVM community here? What are you looking for from an NFV platform? How big are the typical deployments, that kind of thing?
Well, it's okay.
I think it's on.
Okay. So probably, I don't know if you are very aware of what NFV is. Okay, NFV is an initiative by telcos and providers to vendor providers, okay, usual, common network manufacturers to create an environment for virtualizing all the network functions that currently are running on top of a specific purpose hardware. So KVM in this area is providing the hypervisor layer, okay, to allow us to run all the network functions that we are currently running on top of a specific hardware to run it on general purpose hardware. So this is really important, as you can imagine, because it can help us reduce the cost of the network, okay, because we can deploy all the network functions as software running on virtual machines on general purpose hardware, and that's the big opportunity for KVM.
So you mentioned network functions. What do you mean by a network function in the context of,
Yeah, you can imagine all these big boxes that we have in our central offices, okay, but from Cisco, Juniper, Ericsson, Alcatel-Lucent, Huawei. Okay, so these network functions are big boxes made with their own hardware, or maybe built by third parties, okay, and with their own software running specifically with instructions. I mean, it's code executed for being executed only on this hardware. So network function is every of these boxes that we have in our central offices, okay, but instead of doing it by hardware, what we want is to do it with software. So network function is a router serving, I don't know, tens of gigabits per second. It's an EPC. EPC is, let's say, mobile edge, okay, for thousands of users. Is it also, I don't know, an IMS SIP front end? This is a network function. Network function is every box that we have in our central office. Okay, that's a network function.
So it's essentially everything that a telco does, right? Voice,
yeah,
data,
right.
Cellular, broadband.
Totally right.
Okay. And in that world, I think one of the, and I should thank OVA, Open Virtualization Alliance. Thank you very much for sponsoring this panel, by the way. And in that world, in the telecommunications world, there are a number of performance constraints that get imposed on the hypervisor. Some of those performance constraints, I understand, are throughput related, either packet throughput or byte throughput, data throughput. Some of them are latency related. You need very low response time. And some of them are jitter, right? Determinism related. Yeah. So can I spread out through the panel here? Vincent, perhaps. Can you give an example of something that would require the kind of the additional performance related to something like throughput that you would give through something like a DPDK offloading?
Yeah, for instance, we see cases where you need gigabytes, tens or hundreds of gigabytes of IPsec. Typically, you say you have a box, and the IPsec gateway segregates some traffic from inode Bs to the core networks, or from users to the core networks. And in such case, we run the virtual IPsec gateways as a KVM guest, and it means the guest needs to sustain. You have a servers with 2 to 4 40 gig interfaces, and you need to aggregate about 100 of gigabits per second of IPsec throughput in a case. That's one case, and it can be some virtual firewalls and same. It's always packet rates. Usually, we see packet rates start from 10 million of packet per second up to 100 of million packet per second. Just always keep in mind this managing chamber: 10 gig, 15 million packet per second; 40 gig, 60 million packet per second. So that's what we have to sustain. We are not talking about the 100 of kbps.
And another thing, the real-time constraints on the kernel. What kind of network functions would require real-time constraints? Perhaps, Steve, that's a good one for you.
So when we talk about NFV, particularly obviously from my point of view coming from the OpenStack world, what we see is the initial use cases within the service providers. It might start off with the IT organization, then it moves into the networks, starting with those that have some of the lower performance constraints. And then as we start to see people, particularly from the wireless and radio businesses within the service providers, looking to move to OpenStack, and underneath that KVM as the hypervisor, that's when we start seeing the requirements for consistent and deterministic levels of latency. So perhaps taking that trade-off where you use a real-time based kernel and you have arguably higher latencies on average, but consistent, and without that, the jitter and the peaks that you see without the real-time kernel.
Okay. Anybody else? June, perhaps you've mentioned real-time constraints and the kinds of things that you would need to do in a guest for VM.
Yes, what am I hearing from our partners, are like sub 20 microsec upon arrival packet to the data center. Then you process and send out packets.
Okay, and that's for a use case like radio access?
Yes, and the other thing I want to, mention is the why they want to use virtualization, right? What they are looking at is a dynamic resource allocation. That is what virtualization is good at. For example, depending on the tide, how users are using, traffics are going on depending on day over the time, like in the morning, or if any accident happens, then you need to allocate more resources to increase the traffic, right? So that's kind of dynamic resource allocation is something they're looking at, and that's one of the benefits of virtualization in the KVM.
Okay.
Yeah, I would just to add to that, the consolidation ratios we're talking about in terms of the number of virtual machines that are going to be on a host, particularly for the high throughput workloads, are not particularly. We're not particularly overloading those machines with many VMs necessarily, but it's that ability to move them around the environment, and particularly compared to the boxes we're talking about earlier, the time to provision is much shorter than going through a long procurement process to pick up a new network function from a hardware vendor.
So it's clear that performance is key, and I think a lot of the features that have been coming through the KVM pipeline for the last 6 months or year, and which are in planning, are related to improving performance. I guess a number of things that have happened recently are things like huge page support and vCPU and IO thread pinning. So that's great NUMA awareness. How has that made KVM better for your use cases, Gerardo?
It's clear, okay, maybe you think that Telefonica is not, we don't have any expertise on software development, but it's not true, okay? We were doing our own network functions based on software, okay, from 5 years ago, our team, And so we are very aware of the type of capabilities that the hardware can provide. So we started running some software directly on top of bare metal hardware, okay, general purpose servers, and we started improving the performance. And after that, we thought, okay, let's move to a virtual machine, okay, and let's see how it works, okay. And when we started with the oldest Intel architectures, okay, we saw that, okay, maybe the performance is not that good, okay, but once KVM was adopting all the hardware assistance, okay, or hardware support for virtualization that the chips from x86 architecture are providing, okay, we found out that the different gaps were being solved. And right now, there is no difference at all between running a virtual machine, okay, and running, a software on a virtual machine and running it directly on top of the hardware. So it's clear that the gap in this has improved a lot, okay. There is some room for improvement still. I think that new architectures I know better the architectures from Intel than from AMD and other providers, but for instance, there is something called QoS cache that allows you to split layer 3 cache that is right now shared by several VMs, okay, in the processor, and it could be good to be able to exploit that capability to split the cache so that each VM, 2 VMs, for instance, in the same processor, running in the same processor, could have performance without affecting one the other.
So there are a couple of controversial topics when you start talking about performance in KVM. I want to get into that now. And this is the point of this is to create a dialogue between people who are working on NFV as a use case for KVM and you, the KVM community. So I would like this to be a little bit interactive. I don't know exactly if we have a microphone that can go around the crowd, but please do stick up your hand and ask questions or make contributions here. One that's been I've noticed has been controversial is how do we accelerate inter-VM communication, right, at the broadest level? Is something like an IV shared memory approach, or is it something like a VM func that you were proposing to allow kind of memory to be protected within a VM and accessed by other VMs? Which is the best approach to accelerating, or are they incompatible, right? Which is the best approach to accelerating communication between VMs? So June and Vincent, I know that you have differing views here, and I also know that some of the community here have some very strong views on all of these topics. So I'm going to just... Vincent, do you want to go first?
Yeah, thanks. So yes, right, it's a hot topic. So I'd like to comment just on the NUMA stuff. You're asking what it's used for. I mean, there's one thing I've seen until recently. Before the evolution of QEMU, we were in let's say a quad socket system. We were launching 4 QEMUs to be able, let's say, to have efficiencies. And now we can move from a case where we have 4 QEMU to a single QEMU. So it's, from management point of view, it's much more efficient and simplifies the management. So now back to the VM to VM communications. I'll go at 2 levels, still related to NUMA. We have a problem today. We are not able to do VM to VM communications when the VMs are on 2 different NUMA nodes efficiently. So that's there are a lot of QPI, if it's Intel bus or system or others limitations. Now on a single socket, so what we see is that we have needs of sustaining. We have a memory bandwidth of more than 500 gigs per second with an Intel servers. So it's much more so what we can get with the PCI bus. So, which means that when we want to communicate from VM to VM, the industry has been trying to go through the PCI bus and to do some external switching, either on the PCI board itself or on the type of rack switch. And the conclusion was that every time you go through the PCI bus, you have at least 0.8 microsecond latency. You are limited by the capability of the PCI routes. You are tracing your IOTLBs. It was just a nightmare. So we all converged to the solution, okay, we need direct VM to VM communication, so either through the host or direct. So if we go through the host, we are overloading the kernel from the host, could be the Open vSwitch, the Linux bridge or whatever. So now we go direct to the VM to VM solutions. So we need something that allows some kind of memories and mappings. And of course, the first of choice has been IVSHMEM because it was there in QEMUs. I mean, we have through the bar zeros the capability to do some notifications. We have the ability to define data structures. It's well used. I mean, I'm coming from some area of HPC, and I have a lot of friends using that in France. In the HPC, they are used to share some database in the shared memory and to do some compute on different VMs on the database. It's kind of so it made a lot of sense to apply that to networking. And our findings was that through such mechanisms, we were able to have things like 7 to 10 million packets per second minimum of throughput through the DPDK frameworks. So okay, that's good. Let's go that way. Then maybe we need to consolidate it because it's like, for instance, if you look at DPDK, there is a memnic approach that is from NEC, and that Sixwin has been supporting. Then we are looking to do it even more efficiently right now. I'll be talking about that later on. I know, John, you did propose something trying to remap the VRTIOs through the VM funk. Let's say, for me, at the end, it doesn't really matter. What is important is we have to use the capabilities of the memory boundaries. That will be fundamental. John, if you're...
Okay.
At least, I question for you that in your logic of VM to VM communication, when we go through the M monitors or the VM funk, as you raised, I think it was on Tuesday, the latency is about 150 nanoseconds, which means at 10 million packets per second, at 60 million packets per second, and even higher. I mean, it's still too bad. So what could be the other options? I mean, can we really use that capability of the as well? And more, by the way, not all the processor does it, so we need a solution for as well, but we need solutions that are, let's say, CPU generic at the same time, like that will work on ARM CPU, on AMDs, and others. So,
well, I think, first of all, in terms of inter-VM communication, we have two things. One is data movement, and also notification stuff.
Yeah.
Right? And notification, you need to across the VM boundaries, right? And today, the benefits of virtualization, the goodness of virtualization is isolation. But because of isolation, the notification cost is actually high. So how can we overcome that kind of boundary isolation without losing security or anything, right? So we are working on that kind of thing. For example, posted interrupt, other thing, but posted interrupt still, it's basically interrupt. So interrupt goes to the guest kernel, or then if you have a user level program or application to handle packets, then yet another translation. So it would take another transition and latency. So that's one thing. The other thing is, like I said, the data movement. If you copy data, the mileage you get is limited, right? So you want to avoid, the copying.
It's still better than the PCI bus.
Yeah, and there are some technology to copy data without hurting, CPU cache, for example. Okay, but in any case, again, even data movement, we have VM because of isolation of memory space, right? So in general, the VMs cannot share memory. Then we have the IV, SHMEM, right? Which basically allows the VMs to share memory. Okay, that's the IBH SHMEM, and then, however, there are some concerns among our users and OEMs with the shared memory. For example, DPDK. I don't want to, scare. I don't want to scare you guys, but in DPDK, they have a huge 1 gig shared memory, basically. And all the packets and data are shared by all the VMs. So in a way, DPDK application on VM can take a look at the packets for other VMs. That's the kind of consequences of using.
From use case, we did disable that.
Yeah.
Because we prefer to have RTM MBUF pools per VMs, and then to have a kind of mailbox and mem copies between the two. That's much more efficient.
Yeah, so there are some way to kind of avoid that kind of problem, but in general, I'm talking about in general problem with the shared memory, and then other thing is what you can do with shared memory is basically just a shared memory. So you cannot, for example, run code, special code there. You typically just what I propose, at the KVM forum was the VM Funk, and the VM Funk was initially designed for security applications. The purpose is for an application to have secret data or island of data inside the application. And even the application, even the host kernel, the guest kernel, cannot take a look at the data, okay? And that is done by the coordination with the hypervisor. So hypervisor set up additional special translation, EPT translation for that application, and within that application, the data is accessible. Okay, so that's the only data side, but by extending that, we can actually run the code in that trusted view. So for example, if the hypervisor allow the guest, trusted guest, part of a trusted guest, to access others, memory of other guests, then that guy, access the memory of a remote memory at runtime, basically, any memory. So that's one, the kind of benefits, and also.
How will that work with any CPUs? Because that's very Intel as well specific.
Right now, this is Intel only, and even when the Intel only, this is available on the latest hardware. Yes, so but you can implement in that in software.
I would like to go to our audience at this point and make this a little bit more interactive. Can I borrow a microphone off one of you guys? And thank you. I'll do my Jerry Springer impression. Does anybody have any questions or comments related to this topic specifically? How to accelerate inter-VM communication, or yes?
Told you. Hi, I'm Ronen from Red Hat, and we did an experiment with the Ivy shared memory with Memnik versus VLStuser and Virtuonic. And Marcel did it, he sits over there. And it turned out that the solution of using VLStuser and Virtuonic outperformed the Ivy Shmem memory. Oops, excuse me. So this is what our preference is, and we're pushing that, so just for your knowledge.
Let's say there is a kind of confusion. You cannot conclude that because Memnik is not efficient, it means Ivy/Mem is not efficient. It's not right at all. The problems come from the Memnik designs. So I know Shimamoto-san has been trying to optimize it. We are experimenting another approach at 6 Winds, and we found that we were able to get with other data structures and other data movements with the shell memory, which is much faster than the Memnik's logic. So the conclusion of that is that we are opening a huge areas of a kind of defining options. Could be through the VM funcs, means we could define a specific standard, or Virtio, or through the shell mem we could define a specific standard. I mean, there are rooms for any innovations in the shell memory to find solution with the processor that can be efficient. So I think that's what it is important. We should not just conclude that, Okay, VS users is nice because that will work with with Windows, with FreeBSD, Solaris, and so on as a guest right away. But then when we need very fast data movements, we need to let freedoms to the applications. I can do networking packet movements, that's Memnic. I can do efficient packet movements, that's what we're trying to do right now at Sixwin. We can do some database data movements through the shared memories. Nobody knows what kind of innovations we may see.
Is there an incidence of packet size? Do bigger packets?
It's not network. It's not just a networking question. I mean, when we talk about VS users means networking. When we mean IVS/MEMS, we mean anything. And Memnic was just one small case. But I would be very interested to see the numbers that you on the QEMU mailing list. So people, and since the same on DPDK mailing list, so you could have people from Sixwin and NEC that I guess could argue about that.
Yeah, one comment from hardware point of view. Actually, the platform has a DMA engine, right? For example, Intel, and NICs are using that kind of DMA engine and without hurting a CPU cache. So it's possible you get some advantage if we use a special DMA for just the data movement. Because if you copy data or something, then that easily you hurt that cache, right? So, and the inter-VM communication is sensitive to cache and the TLB stuff. So if you don't affect those or hurt them, that's sometimes you see better performance with the other DM engine.
And what about having some kind of read-only models of shared memories, different, let's say, different capabilities where some area of shared memory from a guest point of view is read-only, and from another guest it's let's say, read and writes. So we could find some maybe some secure data movements between the guests without really memory copies, in fact.
Mm-hmm. So we have a question.
Most of the NFV materials that I've read regard using Linux as a guest. Since you're like with DPDK doing a lot of things in ring level 3, so in user mode that are actually like more similar to driver development, have you considered using a different OS like OSV, for example, as the guest for NFV? So that everything runs in the kernel and you don't have ring 3, ring 0 separation at all?
On my side, it's a bit question mark, you're right. I'd like to see that.
So, Jun, you mentioned in your presentation the day before yesterday that the packet size was quite small, I remember. Is that typical for the NFV use case, or does that vary from use case to use case?
Yeah, compared with conventional data center workloads, that's what we are hearing. They tend to use smaller packets. I think you have comments on the packet size, right? More.
Yeah, the point about the packet size is that, there are two things here. One, it's difficult to convince someone that the software running on a general purpose hardware will behave in the same way as software running on specific hardware. So when we started with this, I think that all the comments about the packet size is because in the very beginning they were telling us, the packet size with the small packets, the performance will be poor. So that's the reason why we are always struggling with these small packet sizes. In real network, the average packet size is, I don't know, from 700 to 1,000 bytes, more or less, depending also on the direction. But the idea of the packet size, I think that the most important idea is that maybe there could be a kind of denial of service attack, that could affect, the network devices. If someone or 2 or 3 people with fiber optic, or maybe more, can generate enough packets, per second with small packets, that could somehow starve the network function, the network element.
Yeah, here when you're talking about NFV implementation, as was mentioned in the previous question also, you are talking about NFV implementation in user mode or it's in kernel mode, and how you deal with VM exits, and when the packet has to be transferred from the user mode and to the kernel mode. So what exactly is your point, NFV implementation, whether it will be in user mode or kernel mode? User mode, I mean, will it be part of like a user mode separate process where you are implementing NFV, or it will be something like you implement in host kernel, like routing, load balancing, and all that stuff?
Yeah, I think it's implementation specific. Some, existing solutions, may have huge, user applications, millions of lines of code. And when you do complex things, it's better to use, user land rather than having a, big thing in the kernel, right?
Any performance marks or something you can suggest? You can suggest what should be the preferred way for a server like for a data center like environment, whether it should be implemented in user mode or kernel mode, and any performance numbers or any suggestions?
Maybe it would be useful for Gerardo. Can you explain like a typical EPC, for example, how many components there are in that, how many servers that would typically require to do the whole EPC core?
Okay.
Just
EPC.
to give an idea of what kind of applications we're talking about here.
Okay, maybe it's easier, maybe APC or a fixed network node. Okay, it's something that has to deal with thousands of users. Thousands of users is like tens of gigabits per second. So more or less, what we are testing in our lab. Okay, right now are VNFs that are able to support 40 gigabits per second. Okay, with small packet sizes, 200 bytes. Okay, and this means that we are using very, very big VMs, okay, that run, that's the size of the VMs, and they are running always. In our case, most of the cases are user mode problems, but it could depend. Okay.
I may have, Dave, another examples of very big VMs and depending packet size, where it's kernel, compute, user, and everything at the same time, which is the VBRAS or VBNGs. I'll say not the simple one when it's MPLS or GRE traffics or QNQ, and that's the easy one. I mean ones which is L2TP or PPP. As you know, an L2TP, a PPP stack is a nightmare. L2TP is a nightmare on top of the nightmares. So you could have a PPP kernel stacks that's good for a few sessions. L2TP kernels has some good ideas. But then when you need to mix the data plane with a kind of a control plane, all the LCPs of the PPPs, then you see, let's say, tens of thousands of transactions between the kernel, the users, where, let's say, some kind of DPDK kind of applications are running. And these guys, which are the end users, are even worse. They say, I want hundreds of thousands of PPP sessions on a server that they're opening as fast as possible. Just in case the network shut down and restart, they want to have thousands of sessions per second, which means plenty of control packets per second. And while the users are opening the sessions, once it's open, we start the traffic which is shooting the system. So it's like a DDoS from the users every time.
So before we wind up, I also want to touch on, Steve, you mentioned real time earlier, and the trade-offs between determinism and median performance or mean performance, whatever. What are those trade-offs? Is it possible to include real-time patches for a KVM without degrading the general case?
I think that's really the million-dollar question at the moment, is that I don't think we have a clear enough picture of exactly what the absolute best we can do with KVM as it is before the inclusion of the real-time work. And I think that's where there's kind of some exploratory work going on at the moment in establishing both the baseline performance for KVM when it's fully optimized, and then the baseline performance when you optimize for real-time.
I have a general note. Maybe Intel don't like me now. Generally, we at NEC Lab in Europe, we are also trying different ways out for addressing the NFV issue and high performance. And we are actually figured out that using specialized VMs, something like OSV and MinUS and things like that, plus a network I/O pipe based on NatMap, which actually just maps the memory regions that is used by the host kernel, where the NIC does the DMA requests, and if we map that through the guest and let the management still handled, so meaning the network driver handled by the host kernel, and have some notification scheme which batches packages, something like that, we get quite really promising results of that, even without having EV shared mem implementation or something like that. So reducing the overhead in the guest operating system by just having a single address space, by having nice notification scheme and access just to the critical memory region where the packets is, but not to the full, critical regions is, in our research, enough already to get line rate performance on current commodity hardware.
We did some equivalence where we did initialize inside the IVSH MEMS the memory mapping. So when we do a VF transfer DMAs, it goes directly to the guest and to an area which is directly shared between guests. And then we get to some fancy issue with the DMAR of the system, because then you have two VMs which are sharing a kind of same VF. So I don't know how you did manage that.
Actually, we saw that it's sometimes even more expensive to reprogram the NIC all the time, the NIC descriptors, to map to different addresses in terms of performance. So it makes sense to keep the NIC descriptors pointing to the same addresses and do actually a packet copy. And even our software switches.
That was our conclusion too.
Exactly, yeah. If you do then communication from one VM to another, we do a copy there, at least one. Or just one. And actually the copy itself is not really that an issue.
So my other question is whether there is any work done in the guest, so not really regarding virtualization, but that can also help minimizing the workload and the number of VM exits, and so give a bigger benefit in the case of virtualization. For one example, could be the patches to run CPUs without the scheduler tick. Would work like this benefit NFV even more than bare metal applications?
At least I will say anything that removes ticks is welcomed. Because we are really talking, I mean, we see cases on the market where we are talking about 5 microseconds, 2 microseconds jitters on the system itself. So even the BIOS become a nightmare, because when you benchmark, yes, you got your 2 microsecond delays, but then suddenly the XCI shows a packet which is 1,000 microseconds for any reason. You know, oh, maybe there was a tick, but sometimes it was from the BIOS. You
mean like system management one?
Yes.
It's possible.
And as to that guy to fix, please.
I have a question about, I think we started off in the corner with on the edge of the network where you are communicating with the outside world and having a box that does some routing or having some routing function. What about hardware virtualization? Do you have any viewpoint on that? I mean, SRIOV type of pass-through devices instead of emulating in software. What's your viewpoint on that?
I thought you have Intel on the panel, but we're opening a troll. I will say SRIOV is a marketing solution from my point of view, but when it goes to real life in the data centers, it's the beginning of the nightmare, because you create a lot of complexity in managing it, because it means that each VMs get exposed directly to the top of rack switch, so which means that any SDN features, think your VXLAN or whatever, has to be managed directly from the top of rack switch. And what you want to do when you build your data centers, you want to optimize the cost per 10 gig or 40 gig ports per compute nodes. So SIOV just push you to buy more PCI boards or more top-of-rack switch.
Is live migration with SRIOV and PCI pass-through a concern?
It's not concern, but you can fall back to
need.
software anyway, anytime. But the kind of issue with the SRV is One is the virtual functions. The functionality is simplified and limited compared with the physical NIC, actually, physical function. And also they typically has a virtual Ethernet switch, right? But that's also kind of limited. So in practice, you need to fall back to software anyway. And that's kind of problem. So you know, again, the solution will be software, not
There is a solution to that problem where you mix, let's say, kind of direct PCI pass-through with the guest and the NIC, is to use what we call some smart NICs. When you run a Linux-based system on smart NIC, like using some KVM Octet on Talera or Broadcom, there are some other CPUs showing on the parquet. And where on that CPUs, you do your packets logic, VXLAN, whatever, to communicate directly the packets to the guest. And then on the guest, you don't need to have any compute on the CPUs. So it's really a trade-off. Where do you want to put your compute? Do you want to put it on the smart NIC, or do you want to put it on the cores with the hypervisor? And then, in that case, I was saying SIOV is bad, but in that case, SIOV is nice.
Yeah, actually, we at NEC agree with that. That you need a software switch in between, especially if you imagine VM to VM communication, if you have your data center and then the leaf nodes are communicating to each other. If you would use completely SRV, you're limited by the PCI bus again. You put a lot of traffic to the bus itself, right? Just for traffic that keeps within the host. And the other point that we see is actually this allows you a bit in flexibility as well to run your virtualized network function on a different hardware, because you need support for that specific device that you have there.
So I'm conscious that people are probably looking forward to Daniel Béranger's presentation afterwards. So we're running out of time. So is there maybe time for one last question from the audience, or one last? Who's telling me when I'm out of time? Karen? I'm out of time. So just to round up, can I, for each of the people on the panel, just last second, starting from Stephen coming towards Vincent, one feature request for the next cycle of KVM related to NFV?
So I think all of these guys are going to say network acceleration. So from my point of view, I think that analysis we're trying to do around the real-time work is really the next phase, or the next big phase anyway.
Jim?
And in addition to what Stefan said, real-time, and also the fast and the secure inter-VM communication.
Improve VM isolation through QoS cache.
Don't use VM.
Well, I would say that's probably not very useful for KVM.
On KVM, but yeah, use some Docker or containers.
Okay, so KVM to add Docker support. No? Yeah. Thank you all.
Thank you everybody for listening to this. Is this?
I don't know if that's on. Thank you everybody for listening to the panel, and thank you to my panelists, and thank you again to OVA for sponsoring this session. Thank you.